Hello everyone. Today we'll be solving the NotOptimisticPortal challenge from Ethernaut. Before we begin, I'd just like to say that usually I like these videos to be as intuitive and well explained as possible. However, for this particular problem, it's going to be very hard to do because it's very technical and it requires a lot of reverse engineering of code. So I'm going to be stating a lot of things more or less as facts with little explanation. But at the very least, we will have a working solution, and I hope we will still be able to shed some light on the various concepts that are involved here. So let's begin. We are told that the portal relies on a complex chain of cryptographic proofs to verify cross-chain messages. It claims to be secure, but there might be a gap between verification and execution. And our goal is to mint some tokens for our wallet. And things that might help are function selectors, CEI pattern, Merkle Patricia tries, and RLP encoding. So those are the things that we will need. And as you can see, I've already opened a few tabs here above. So I have, for Merkle Patricia tries, we have the classic diagram here from Ethereum, where we see that we have three types of nodes. We have extension nodes, we have branch nodes, and we have leaf nodes, and they have different properties. So we're going to be referring to that. And we will be using the library. So here the problem gives some Ethereum optimism library. So they're giving us basically the RLP reader, and they also give us the secure Merkle try. So I have them open here. So this is the secure Merkle try, which more or less just refers to the regular Merkle try, which I have opened here. And we have the RLP reader and also the RLP writer that we will be using for all of the RLP encoding. And without further ado, let us just open a window in Remix. And in there, I will, as usual, paste all of the code. And we'll start by compiling the contract and trying to work out a strategy of how we can solve this problem. So I will create a file, NotOptimisticPortal.sol, and I will paste the code. So, of course, in order to have the reader, we need to have the correct link. So I believe reader is here. And I will just replace it. And as well, secure Merkle try. So here we go. And that appears to be it. So our contract compiles. And I would right away like to have an attack contract because we will need an attack contract. So contract attack. And yeah, I'm not going to write anything for now. So let's take a quick look at this contract. So we're told that our goal is to mint tokens. And let's just see if we can find the mint. Where do we mint? So this is the only place where minting occurs. So if we get to this point in the code, the mint function gets called and we mint this amount of token to this token receiver. And this occurs in this execute message function, which takes in token receiver amount, message receivers, message data, salt, something called proof or proofs, and a buffer index. So basically, if we can call this function and if we could get to this point of the code, we are done. And I think it's also worth it to look at the constructor, where we see that in the constructor, we receive some kind of RLP block header. We receive name symbol, but mainly this RLP block header, from which a bunch of data is extracted. And we basically update the L2 state with all of this data. And so this would be the equivalent of mining a new block and attaching it to our chain. And in particular, this new block will have a state root here, which is going to be the hash of some data. So I would say that the first good idea would be to perhaps fetch this RLP block header, as was called in the constructor. So I'm just going to go ahead and get my instance address. And I'm going to go on Sepolia Etherscan. And okay, I'm going to go into internal transactions. And as usual, advanced mode. And here I need to do a little bit of research. So, or not research, but I need to basically find it. And in particular, here, let us see. So this constructor receives a governance address. So let me just actually see what is the governance address by kind of deploying this particular contract. So if I go here and I would like to switch to the Sepolia testnet, and I would like to go to the NotOptimisticPortal at this address, and I would like to get the governance. So this is our governance, and I would like to search for this address. And yeah, so it's here. So I think this is the right call for the constructor. So I'm just gonna go ahead and paste it inside a comment. Let's just show everything. And again, let's try to find it here. So this particular address is a static type. And from the constructor, we are looking for a dynamic type. So we're looking for bytes memory RLP block header. And right now we're seeing address governance. And so the content of dynamic types is contained in the tails, which always come after, whereas the content of a static type is contained in the heads. So basically, we need to look after this particular string, or address, I mean. So if I'm just going to press enter, and we see that here we have an 8, and 8 would be the length. 8 would be the length of this name string. And then after that, we have our actual name string. And then 4 will be the symbol string. And then the next 32 bytes will be the symbol string. And finally, this is what we need. So we are told that our RLP header is of length 207 in hex. So 207 basically, and this is, I think, all of the rest that follows. But because this is kind of in blocks of 32 bytes, and 32, so basically the 2 here is a multiple of 32. So we just need to take the 7, and 32 minus 7 is 25. So we need to take off 25 padded bytes from the end. So, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 18, 19, 20, 21, 22, 23, 24, 25. Okay. Don't really like doing that, but I guess here we didn't have much choice. So this is basically what we want. And let's just check very, very quickly in perhaps our attack contract. So I'm just going to do a function. I'm going to call it getSig because public pure, because we will need this later on. returns, let's just say bytes, or let's just say returns uint 256 for now. And here we will say bytes memory RLP header is equal to hex. And we will paste this. And then we will return RLP header dot length. So we will compile, and let's just check it on something like Remix. So let's deploy the attack contract and just make sure that, so 519, and we will need to know, so 207, let me just grab a calculator. So if we basically, 207, that's 16 squared, times 2, of course. 16 squared times 2, and plus 7 is going to be 519, and indeed we have a 519. So this is the correct RLP header. And at this stage, I think it's a good idea to start mapping out how we're going to solve this problem. So this RLP header contains a lot of information, but in particular, it contains a state root. So basically, if we go back here, there's a state root that is extracted from this RLP block header. And this state root is a hash. And unfortunately, we cannot know, or we don't know, what data hashes to this state root. And why is this a problem? Well, this is a problem because in order to pass this function, this execute message function, our proof will need to, like part of our proof, will have to hash to the root. So we have to know the data that, when hashed, produces this state root. And I mean, you can trace it through the code, but for example, when we verify the message inclusion, we pass in a buffer index, which is likely going to be 0 or perhaps 1. And here, whenever we are doing this buffer index, there we go. So the state root, which was extracted in the constructor, is passed in here, and it's passed into the verify inclusion proof. And this basically trickles down eventually to down here to the function, I believe it's called walk node path or something like that. Yes. So there's a function called walk node path, and inside of this function, basically, if we are in the beginning, if we have a first proof element, it always has to be like the root node, and we will require that the catcheck256 hash of our current node is the current node ID, which in fact will be the root. So all of this to say that we are a little bit out of luck. We're not going to be able to solve the problem simply by using this RLP header that we have. We need to do something else. So what do we need to do? Well, in particular, if you look at the contract, we have many functions available to us. So we have, for example, a function which allows us to submit a new block. And this new block basically takes in a new RLP block header. And from there, we extract basically the same things, including the state root. And if we can control this block, if we can become the sequencer, and this is only for the sequencer, we can submit a new block. And if we can submit a new block, which is our own block, which is under our control, we can also produce a valid proof for that block. So the question is, how do we become the sequencer? Well, we also have an update sequencer function. And in order to update the sequencer, we need to be the owner. And in order to be the owner, well, we need to update ourselves as the owner. So there's a transfer ownership function here, which is, you have to be an only owner here. You have to pass the only owner modifier. And the nice thing about the only owner modifier is that, in fact, yes, it requires you to be the sender to be the owner, or it can also require simply that the sender is this particular contract, which is basically what we're going to use. The other thing to note is that, well, actually, why is this relevant? How can we actually make this contract, this not optimistic portal, how can we make it call something? Well, we can simply, in our execute message function, we can make our initial message receiver this not optimistic portal contract. And the message data, we can simply make it the transfer owner function. And why does this work? Because if you actually analyze the code a little bit in more detail, you will notice that in order to be able to execute these operations with message receiver, so imagine if message receivers of 0 is this not optimistic portal, and message data is the transfer ownership function. So if we look at execute operation actually requires your call data to be a certain hash, so 0x3869 and whatnot. And this actually turns out to be the function signature of the function that is described here on message received bytes memory message data. But conveniently enough, another function that hashes, or whose signature is exactly this as well, is the transfer ownership function. And I think right now it's simply to just show you rather than keep blabbering on. So this is why I also have this get sig function. And so here I'm going to, let me just make it external first of all. External, and let's have it return a bytes memory. And so first of all, let's just return abi.encode with signature. And let's just have here bytes call data func name. And let's just have it here. And yeah, actually, it's not bytes, it should be a string. So here we go, I can compile this. And now if I deploy this attack contract once again, so first of all, let us check that this on message received. So if I just paste on message received, actually, let me just put in the quotes, and I need to remove this. So if we get the signature of this, we get this particular hash, or let's say 4 bytes. And let me just find, so I'm just going to paste it here, and we see that this is exactly what is required. So basically, in order to execute an operation, your target has to have a function signature, which is this. But funnily enough, and this is kind of the Ethernaut part of this problem, is that I can actually take the transfer ownership function. I can actually take this and if I try to get the signature of this particular function, funnily enough, I get exactly the same thing. So this is obviously a cooked up bug where we can, like, even though under the execute operation, we are checking that our function signature must be this, must resolve to this. As a matter of fact, the transfer ownership function will satisfy this requirement, and we will be able to do this. So we will be able to do everything that I just described previously. We will be able to make ourselves the owner, then we'll be able, or maybe not ourselves, but we'll be able to make our attack contract the owner, and then we'll make our attack contract the sequencer. And then once we're the sequencer, we'll be able to submit a new block. And basically all of that will be done. All of that will be done by the time that we are actually in this point of the code. So in this, we'll be calling execute message. And then in these execute operations, here we will have two operations where we will make ourselves first the owner, then the sequencer, and then we'll submit a new RLP block header, and we will update everything. And basically at this point, our RLP, block header will be updated. And this is where we will verify the proof. And because we control this RLP block header, we will be able to beforehand produce a valid proof for it. And this is where the checks, effects, interactions pattern comes in, because really we should not be executing these operations before verifying. We should verify first and then execute operations. So this is another vulnerability of this contract. The checks, effects, interaction pattern is not respected here because we're executing before verifying. So enough of this chit chat. Let's try to go ahead and implement that. So first things first, let me just see if we have all of the libraries. So I have the secure Merkle tree, I have the reader, but I would like to have the writer because we will definitely need that. And let me just make a writer here. So we have both the RLP reader and RLP writer to do our encoding. Now this attack contract, again, remember, we will be calling this attack contract to execute an action, mainly to become the sequencer and to then submit a new block. So we would like to be, I mean, it's not strictly necessary, but we would like to, for our attack contract to be this, to implement this interface. And we can just add this particular function, which can simply be empty for now. And I would also like to use these libraries, so reader for bytes and RLP items. So there we go. I would like to have both addresses, I guess public, and I can make them immutable, why not? So for the target, which is going to be our instance, and the player. And let's just go ahead and get our target. So our target is going to be our instance address. And actually, I'm not sure why I have two instances here. I just noticed it, but so This is going to be our instance address and our player address as well. Let me just type player. Okay, here we go. There are also some constants, in particular this L2 target, which I will need, and I would like to copy it inside of here. Or I guess we can just access it from the target. It doesn't really matter. And I would also like to have a public RLP block header. So when we will produce a new block header, we will basically save it inside of this variable. And so now the getSignature function is not going to be useful really anymore. And let's just have an attack function here. And we're just gonna make it external. And let us, first of all, initiate basically the message receivers and the message data. So we'll have an array of addresses, which is going to be in memory. Message receivers. And we're going to have 2. And we're also going to have basically bytes. And this is going to be data. So this is going to be our message data. So message receivers and message data. So our first call will be set first call to target the contract to become owner. And so our message receivers of 0 is going to be the target. So we'll be calling the target. And the message data of 0, well, actually, let us just do abi.encode with selector. And here our selector will be NotOptimisticPortal dot transfer. I guess it's not auto-completing. Transfer. Yeah, it's basically going to be this. So NotOptimisticPortal dot this dot selector. And basically, who do we want to become the owner? Well, we want our attack contract to become the owner. So it's going to be address of this. So this is going to be our first call. And then second call, or set second call to this contract to become sequencer and submit new block, basically. So we'll have message receivers of 1 is indeed address of this, and basically in this particular case it's going to be just attack dot on message received, and we're not going to pass any data. And so there we go, our message receivers and message data have been initialized. And let us also now set up a proof. So let's start setting up a proof. So we'll just say not, let me just copy it here. So NotOptimisticPortal dot proof data, which is the struct that we're using. And we're just going to call it proof. And here, let us declare a couple of arrays of bytes, which we're going to be using for encoding purposes. So I'm going to call this memory try proof array. So it's going to be new bytes, and this is going to be 1 of length 1. And then I'm going to have another one, which I'm going to call decoded, and this is going to have length 2. So this try-proof array basically represents the number of nodes. So, let's say if we had 2 nodes, let's say if we had an extension node and then a leaf node, then our try-proof array would be of length 2. So this basically represents the depth of our proof. And the way we're going to do things is that we're going to make things as simple as possible. So our proof, or our tree, if you will be just one leaf node. So we're only going to have a proof of length 1, and our proof node will simply be a leaf node. And this, because a leaf node, if you actually look in this library, in this Merkle tree library, basically they have the length. So a leaf or extension node is of length 2, and so whereas a branch node would be of length 17. But a leaf will be of length 2, which is why I am declaring here decoded, and the decoded is 2, which means that it's a leaf node, and this means that only one node. So this is how we initialize the proof. So the next thing we're going to do is that we are going to initialize storage try proof. So if you basically go back and look at this at the proof data structure, so you have state try proof, you have storage try proof, and you have account state RLP. And it turns out that the storage try proof is the first one that we should set up. And if we go back a little bit further, just to get an idea of where everything comes from, so under verify message inclusion, basically, first we're verifying the state root, and only then we are verifying the storage root. And basically the first thing, or here in this particular case, the path that we want is the ABI encode packed of message slot. And the message slot is passed here as a bytes 32, but in actual fact, when we call this verify message inclusion function, the message slot is actually the withdrawal hash, and the withdrawal hash is basically done using this function. So there's a compute message slot function which is used. So I'm just going to copy this compute message slot function into, which is actually just a pure internal function. So I'm going to copy this into my attack contract. First of all, so just so that we have it. And yeah, so this is going to be stored in the decoded of 0. Yeah, so decoded of 0 will kind of hold the path, uh, that we're following. Or in particular for the leaf node is going to be like part of the key with a prefix and whatnot. But yeah, so we're going to store decoded of 0. And for this one, let's just do compute message slot. And so the token receiver will be the player. The amount, let's just set it to 100. And the message receivers are going to be the same message receivers as we're passing originally. So we're just going to do, message receivers as is. And same thing for message data. And the salt, not particularly important. Let's just put it as 1, 2, 3. So this is going to be our computed message slot. And we basically need to have it ABI encode packed. And we also, message receivers. Right, and I think here I have a small problem. Maybe for some reason I need to have it memory here in order to remove this error. So we have it ABI encode packed. But furthermore, if we just go back and look at this and this storage verification. So basically this hex 01 is the value that we're trying to verify that is in the tree. But because if you actually analyze the code, this in this secure Merkle tree or trie, actually what they do is that they don't just take the key, but they actually Ketchak 256 it. So, and this is kind of what we're doing here. So for this reason, we actually want to Ketchak 256 this as well. And then because we want it to be recognized as a leaf root, and the way it's done is that it's done with a prefix, and the prefix for the leaf nodes, I believe, is simply 2. So we want a prefix leaf even of 2. So we can just do a hex of 2, 0. And we can take these two things and we can just do ABI.encode packed for this particular thing. So this will give us the desired quantity, but then on top of everything, we will need to RLP encode it. So we will need to do lib.rlp writer .write bytes. And this will give us the decoded of 0 part of our proof, of our storage trie proof. And this is kind of what I was referring to later or earlier in the video where this the solution to this Ethernaut problem is extremely technical, and you know, there's really not much to say about this. Like, this just kind of what works and how this library functions, and it's not my favorite thing to do, but you just kind of have to take it as it is. And decoded of 1 will have to be basically the value that we are verifying. And again, from the code, you can see that the value that's being verified is hex 01. So this is the value that we're verifying. So we have to put it. But again, as before, we need to basically do the libwriter write bytes. So we need to RLP encode it. So this is going to be our decoded of 1. And then we have initialized the tri-proof array. So this tri-proof array of 0. And here we're just going to take our decoded array, which we just filled. But we are going to make a list out of it. So we're going to have, again, use the RLP writer.write list. So we're going to write list. And actually, once we have this list, we also want to write bytes. So this is the encoding that works. Again, not going into too much detail about this. And finally, that's basically where we're done. So we're going to do proof.storage try proof. So the storage try is going to be our try proof array. But again, we're going to need to write basically RLP encoded as a list. And there we go. So we have our storage try proof. Now, the next step would be to set up the account state RLP. So if you remember our proof structure, our proof data structure has the storage try proof, which we just did. And next, we're going to do the account state RLP. So in order to have an idea of what our account state looks like, we can actually scroll back down to our problem. And we are being told somewhere that our account state is actually these 4 elements. So nonce, balance, storage root, and code hash. And in particular, yeah, the third element is the storage root. Yeah, I guess let's go ahead and work with that. So I'm going to, again, initialize an array in memory, which I'm going to call account state RLP array. And it's going to be a new byte of 4. So we need 4 elements, like we just said. And so the first, so let's just set the first element. So we said that the first element was the nonce, and let's just say the nonce is 1 to 3. It doesn't really matter what the value is, but we need to basically encode it correctly. So we're going to do ABI encode, which will transform it into basically bytes, or a UN256. And then we'll just do the regular RLP encoding. we're going to do write bytes. So we're going to do this, and I'm just going to paste it 3 times here. And we're going to have 1, 2, and 3. So the second is going to be the balance. Again, the value doesn't matter. So this is nonce, and this is balance. So 4, 5, 6, the value itself is not too important. However, this is going to be the storage root, I believe. So this actually value here does matter. And here we're going to do basically ABI. Let me just, I'm kind of tired of this, of these things, or I guess view, sure. Well, it's not going to be view, but I'm just going to put it view for now, just so that I don't have the yellow squiggles. And here, basically, we're going to do ABI encode of, so here we need to use the RLP reader, and we need the read bytes method. And we're going to get the try-proof array of 0. So this is going to be basically the encoding. But actually, we're also going to Ketchak 256 this. And so here the reasoning is that we're basically, we need the storage root to match with what we did in the proof. So this part here is basically our node. So this is our node, and we need our storage root to basically point to that node, which means that we need to set the storage root to be the hash of this particular node, if that makes sense. Again, I know it's not, it's very technical here, but this is kind of what works. So this is a storage root. And finally, the code hash, I don't think it matters either. So we can just do a hex of ABC, for example. And there we go. So finally, we will do a proof.accountState RLP. And yes, I do believe this is the correct thing. So we're just going to take this account state RLP array, and we're gonna RLP encode it as a list. And so finally, the next thing is that we need to initialize the third element of our proof, which is the state try proof. And so this is going to be quite similar. So decoded of 0 and decoded of 1. So for, actually, maybe I can just go ahead and copy this value because the encoding is quite similar. And yeah, actually, maybe I shouldn't have done this, or sorry, I did forget this. Okay. So we're gonna write bytes again. We're gonna ABI encode packed again. We again want a leaf node. We just want a leaf node. We want to keep things as simple as possible. However, this Kachak 256 here is going to be a little bit different. So really what we're doing here is that we want basically the key that we need to verify down there in verify message inclusion for the state root is going to be this ABI encode packed L2 target. So this basically this 424242, etc. So I believe this is what we need to put here. So just ABI encode packed L2 target. So that's good. And basically what are we verifying? So before our decoded one was just basically this hex 01. But now what are we actually trying to verify as in terms of value? And it's actually the account state RLP. So before it was the hex 01, but now it's the account state RLP, which which actually we just got. So let me just go here. So this is a state try proof. So it's just going to be proof dot account state RLP, which we just said here. So this is going to be that, and I think the rest is going to be very, very similar. So we're reusing this try-proof array in exactly the same way. So now we filled out our decoded in a different way. And basically we're going to do proof dot state try proof. And yes, I do believe we're just going to write a list of try proof array, which we again updated here. So now, finally, after all this, I think we do have a valid proof which will pass, given that we reuse the same information in the rest of our code, especially when we submit the new block. So now, basically, we need to do some manipulation as well to set, we need to update the new block header. And if you look at the function extract, I believe it's called extract data. So we see that they do something like this. So they basically take the existing RLP block header and they convert it to RLP item, and then they read a list. So we're going to do something very, very similar here, except that instead of taking the RLP block header, we're just going to take a bytes, and then we're just going to take whatever we read on chain. So basically this big hex value. So we're just going to put it here. And so this is going to be this is basically the old header. And we are going to adjust it slightly. So we're just going to have a bytes memory. We're going to call it in. And it's going to be a new bytes array. And the size is going to be header.length. And here we're just going to do a little for loop. I less than header.length. And if you basically go back, I think it's an extract data as well. So you basically know that the parent hash is at 0, the state root is at 3, this is the block number, and this is the timestamp. So these things, if we're going to submit a new block, these things have to be updated. So I'm just going to do if I equals 0, and then else if I equals 3. I equals, I believe, 8. And then else if I equals 11, and else. So if I equals 0, so this is basically the parent hash. So parent, or actually I'm going to do this inside here. Parent hash. So here I'm just going to update the in, or I should just do in of I. So here basically we're going to take the NotOptimisticPortal target, and we're going to read the latest block hash, which is a public, basically a public variable. So basically here what we're saying is that the latest block hash has to become our parent hash. But as usual, we need to RLP encode everything. And well, actually, I think I need to do abi.encode first. And once it's ABI encoded, I need to do lib RLP writer dot write bytes. So this will set us the correct parent hash. This will be the new state root. So here I'm going to set ln of I, oops. So at this point, I still have basically the try-proof array here for the state try-proof. And so I need to take that and I need to do RLP reader dot read bytes. So I need to read the bytes from this array. And I basically need to catch-act 256 that, which gives me a bytes 32, which I then need to ABI.encode. So again, this is just that, the state root has to be a hash of something. And in this particular case, it has to be the hash of the state try proof, or at least the first node. So I need to ABI encode that. And yeah, finally, as usual, I need to write RLP encoded into bytes. So we're slowly but surely getting there. So hopefully you are still hanging in with me. There appears to be some error here. Oh yeah, so I made a mistake. It's in. So now basically this will be the block number, which needs to be updated as well. And we are, as usual, we're going to have to write bytes somehow. And well, actually, for this particular case, we're not going to write bytes. We're going to write a uint. And here we're just going to take header of I, and we're going to do read uint 256, and we're just going to add 1. So I believe the problem just requires us to have one more, like that the block is at least one more than the previous one. I'm actually not sure. We can probably check it somewhere. I think it's in the submit, or maybe it's an update L2 state. So update L2 state, yeah. So somewhere we require, yeah. So we need the next block number to be one more than the previous one, or the new block number. And similarly, we need the new timestamp to be bigger than the latest timestamp. So this is why we're doing this here. So we need to increment it by 1. And finally, this will be the timestamp. So here, actually, what did I do here? I did something. Okay, so yeah, I mean, we don't need to do anything particularly different, because here I is going to be 11, so header of I, yeah, it's going to refer to the timestamp this time around. And finally, if we're in neither of these conditions, then everything else remains the same. So we can just do we can just do header of I dot read bytes, and that should be it. And once we're done with this for loop, we can update the new RLP block header. And here we're going to use the public variable that we have declared. So we're just going to do lib RLP writer dot write list of in. And yes, and I guess now the view is finally not necessary. So there we go. So we have the proof, and we have the updated RLP header. And so the final step of our attack contract is to actually, execute the messages. So we are simply going to do, yeah, I'm kind of tired of writing this, but yeah, okay, I guess I'll write it. NotOptimistic portal. We're going to cast target, and we're going to call the function execute message. And here, what we're going to pass, these are going to be similar arguments as we passed into the compute message slot. So remember, player 100, and the salt was 1, 2, 3. So these all have to match. So player 100, message receivers, message data 1, 2, 3. We need our proof. And finally, we also need to basically pass in the index. I believe it's called the buffer index. So initially it was 0, but now it's going to be 1, because that's going to be like the index of our of the block header, which we will have just updated. So that's going to be it. And now we need to implement the malicious onMessageReceived function. So we're actually not going to use, we're not going to be needing this message data, since we're just going to be using this RLP block header storage variable. And so by this time, let us just do a quick require statement. Well, actually, let's not have a require statement. We assume that we are the sequencer here, or sorry, we are the owner here. So we have become the owner, and now we have to make ourselves the sequencer. And basically what we're going to do is that we're going to take this NotOptimisticPortal, and I think the function is called update sequencer, and we need to set the new sequencer. There's a lot of code. So it's here. So we're calling this function, and we need to pass address of this. So we want this malicious contract to become the sequencer. And now we need to submit the new block. So once again, we're going to have this NotOptimisticPortal target, and I think it's called submit new block. Yeah, and we need to pass in the RLP block header simply. And so this is going to be our onMessageReceived function. And I could add some require statements here, but I don't think it's necessary. And I think we are good to go. So if we simply compile this contract, and if we switch to Sepolia, and if we try to deploy this contract, so let's just give it a few seconds. And again, if we remember, because we're calling the execute message function, the amount of 100 will automatically be minted, so we don't really need to do anything else. So if we choose the attack contract, I can just press attack. So I need to check out what's happening here. Let's just cancel the transaction. And after looking at the code and doing some debugging, I realized that here we need to read raw bytes instead of just read bytes. Again, not very interesting, just an encoding type of thing. So let's just try to recompile the contract. And let's remove this. We're still on Sepolia, so let's try to deploy our attack contract again. So now that I have gotten some more ETH, let's try to redeploy the contract. And I will simply confirm. So we will wait for it to deploy. And now once again, we should just be able to call the attack function. So it has been deployed. And here we go. We have the attack contract, and we are confirming that we will receive we'll receive some tokens. So that's exactly what we want. And as you know, at this point, we can be fairly certain that we have solved this challenge. But we will, of course, submit the instance just in case to verify. So submit the instance and confirm. And there we go. So we have solved this challenge. This was the last Ethernaut challenge. I know this was a very technical and very tedious challenge, but I hope it got you some exposure to the RLP encoding, to how these Merkle Patricia tries are implemented in real life or in Ethereum, or at least got a taste of it. So in any case, thank you very much for watching, and I will see you next time.